Hello and most welcome to 1563 of the series. We will now take up Epigenetics, and it's an article by Richard A. Jorgensen, and it's coming from Nacional Genómica para la Biodiversidad in Guanajuato in Mexico. It was published in 2011. Can be seen as a sort of an introductory article into what is epigenetics. The perspective presented here is that modern genetics is at a similar stage of development as were early formulations of quantum mechanics theory in the 1920s, and that in 2010 we are at the dawn of a new revolution in genetics. That promises to enrich and deepen our understanding of the gene and the genome. The interrelationships and interdependence of the two views of the gene. The molecular biological view and the epigenetic view are explored. And it is argued that the classical molecular biological view is incomplete without incorporation of the epigenetic perspective. And that, in a sense, the molecular biological view has been evolving to include the epigenetic view. Intriguingly, this evolution of the molecular view toward the broader and more inclusive epigenetic view of the gene has an intriguing, if not precise, parallel in the evolution of atomic physics from Newtonian mechanics to quantum mechanics that are interesting to consider. Physics and the molecular understanding of the gene. In a classic little book, What is Life?, the great theoretical physicist Erwin Schrödinger considered one of biology's central questions. How can a living organism be accounted for by physics and chemistry? In attempting to answer this question, Schrödinger rightly focused on the centrality of the gene, and thus on the necessity of understanding the nature of mutations, given that they are essential for identifying and investigating the nature of genes. Because the chemical nature of the gene was unknown, demonstrating that DNA was the genetic of substance, was published while What is Life was still in press. Schrödinger drew on Max Delbrück's atomic physics-based model of genetic mutation and the structure of the gene. Suggesting that the gene is a linear, one-dimensional crystal. That is, one whose elements do not repeat in a periodic way as in common crystals. Although Schrödinger's little book was not universally well received, especially by biologists, even a critic like Linus Pauling was willing to conclude that Schrödinger's formulation of the theory of wave mechanics in 25 for which he received the Nobel Prize in 33, was basically responsible for modern biology, because it developed largely on the basis of the new understanding of chemistry that quantum mechanics had made possible. Quantum mechanics was certainly also at the core of Schrödinger's speculations on the nature of the gene. What is Life offered a fresh perspective on biology that inspired the new molecular biologists, many of whom had been trained as physical scientists, especially crystallographers and physical chemists. This was the dawn of the great molecular biology revolution that led to a vast increase in our understanding of genes and genomes, and established the fundamental nature of the gene as a nucleic acid molecule comprised of a string of distinct nucleotide bases whose sequence normally specifies a gene product which can affect or influence the expression of phenotype during growth and development. I will now go to the second paragraph of the second column of page 2. Eventually, however, it came to be recognized that simple models based on transcription factors binding to specific DNA sequences were insufficient on their own to explain the control of gene regulation in complex eukaryotes. Molecular tools and approaches were developed that could begin to open a window on the higher order complexities of eukaryote gene regulation. Chromatin was gradually accepted. First as a mediator or modulator of transcription complex formation, and then as an active dynamic participant in the entire transcription process. when the concept of the histone code or the histone language was developed around 2000, molecular biology was beginning to catch up to Brink's 1960s concept of parachromatine. Of course, we are still very far from being able to say that we fully understand the molecular basis of parachromatine. But I have little doubt that we have begun to open the door to a vast realm of possibilities waiting to be explored and to be defined molecularly and mechanistically. The gene as a field of possibilities. The evolution from Mendelian genetics toward what we might call molecular epigenetics via molecular biology's description of the gene as a nucleic acid molecule has an intriguing and perhaps instructive parallel in the evolution of physics from Newtonian mechanics toward quantum mechanics via the planetary model of the atom in which the electrons orbit the nucleus. The original concept of the atom, the fundamental entity of Newtonian mechanics, had held that the atom was an indivisible particle. This concept was transformed twice. First into the planetary model, and then by quantum mechanics, which redefined the atom as a field of probabilities of subatomic particles existing in 4 dimensions. Similarly, the original concept of the gene The fundamental entity of Mendelian genetics was that it was also particulate and indivisible, a concept that has also been transformed twice. First, through the prism of genetics and molecular biology, into the concept of a gene as a nucleotide sequence, divisible by recombination, and now again by molecular biology, looking through the prism of epigenetics into what might be referred to as a field of possibilities of alternative chromatin states. Centered on particular nucleic acid sequence, that is parachromatin, to use Brink's terminology. And thereby Monod and Jacob are proved wrong. There's no program. As mentioned previously, alternative parachromatin states are assumed to be based on diverse chromatin proteins, RNAs, and complexes that can exist in various conformational and covalent modification states that are adopted during growth and development that can differ among loci. In quantum mechanics, subatomic particles may be viewed in two very different ways, that is, both waves and particles. Likewise, paramutations can be viewed both as gene expression states and as mitotically, in some cases meiotically irritable states. Classical genetics and then molecular biology established the micro framework of genetics in the same way that Newtonian mechanics and then the planetary model of the atom established the macro framework of physics. quantum mechanics ultimately led to the idea of wave-particle duality and the description of positions of subatomic particles as a field of probabilities that determine the chemical properties of a given atom. That is, they are not decided. Similarly, Brink introduced the idea of a genetic-paragenetic duality, of genetic loci in which a genetic entity, DNA, and a paragenetic entity, chromatin, both present at each genetic locus, are complementary and interdependent partners, which we might describe as a field of possibilities that determines the expression states of a given locus. In drawing this parallel, I am not trying to suggest that the classical molecular biology view of genetics is neither correct nor useful, any more than Newton mechanics or the planetary model of the atom is neither correct nor useful. Rather, I am simply suggesting that each represents early incomplete descriptions of reality that required important modification and enrichment before we could fully understand the nature of the genetical and physical worlds, respectively. However, we ought not try to take that analogy too far, because at some level of detail it's most likely will break down. Nonetheless, we can explore how far the analogy might or might not extend. Uncertainty in physics and biology. In the 20th century, physics evolved beyond a deterministic view of the universe, postulating that the future of the universe in theory, could be extrapolated from the laws of physics if only one could obtain complete knowledge of the positions, directions, and velocities of movement of all particles in the universe. That's Laplacian demon. Quantum mechanics, especially in Heisenberg's uncertainty principle, raised fundamental questions that challenged the possibility of precise knowledge of the future. For instance, the number of times per second that atoms in a lump of uranium will undergo radioactive decay is known with precision. However, why and when any particular atom will decay is unpredictable by modern physics. Similarly, although geneticists can measure mutation frequency in a particular system under specific conditions, the timing of a particular nucleotide substitution is unpredictable. Only the likelihood of the mutation can be known. Thus, from an evolutionary genetic perspective, biology is no more deterministic than is physics. As Torts has analyzed in terms of population genetic theory. Torts argue that the selective fitness of an advantageous mutation in a population and time comprise a canonically conjugated pair of variables analogous to such a pairs of physical variables, such as the location and momentum of a particle, or the energy of a particle, and the time at which it was measured. he showed that uncertainty is largest at low allelic frequency and when the selective advantage is small. The specific trajectory of such an allele in a population of finite size is well known in population genetics to be unpredictable, and only probabilities for different trajectories can be determined. With the advent of genomics, it is theoretically possible to know with absolute certainty the sequence of a region of chromosome carrying a gene and even the sequence of an entire chromosome. However, as Stadler noted, it is not trivial to precisely locate a gene. That is, it cannot be shown to be delimited from neighboring genes by definite boundaries. This conclusion follows from Stadler's definition of the gene. Operationally, the gene can be defined only as the smallest segment of the gene string that can be shown to be consistently associated with the occurrence of a specific genetic effect. In modern terms, knowing the complete sequence of a chromosome does not allow us to precisely determine all of the many interdependent elements of a gene, including all those elements in cis that are necessary for the normal operation of a given gene. that is associated with a specific genetic effect. In addition, the expression and selective value of a gene in nature may often be dependent on the environment encountered by the organism, perhaps making it impossible to precisely identify the boundaries of a gene. Distinct from quantum mechanics, it is also important to recognize the relevance to biology of complexity theory, which has identified another type of uncertainty in physics, resulting from sensitive dependence on initial conditions, such that relatively simple Newtonian systems may exhibit unpredictable chaotic behaviors due to the impracticality of knowing initial conditions precisely enough. Similarly, it should be evident that knowing all alternative epigenetic states of a given gene in all environments may be unachievable in any practical sense. This is essentially no different than what is postulated in complexity theory, namely that it is impractical to know with enough precision the locations and movements of all particles of a system in order to predict future behavior with any certainty, at least in certain systems and under certain conditions. Perhaps the most we can hope to achieve is to determine or estimate the field of possibilities that comprise the orthochromatic and parachromatic components of each gene. Concluding comments. The marriage of epigenetics and molecular biology promises to deepen and revolutionize our understanding of the fundamental nature of the gene, allowing us to see deeply into its field of possibilities. It is going to be very interesting to learn what degree of knowledge of the field of possibilities that comprise a gene we will be able to obtain. Though I will be happy to be proved wrong, my strong suspicion is that while we were able to learn a lot about a given gene, we can never know what we do not know about it. So thereby dies the programming idea. That is, its complete field of possibilities will not be determinable simply because it will be impossible to anticipate for every gene, every circumstance that an organism may encounter. Finally, given the rapidly increasing interest in the phenomenon of transgenerational inheritance of epigenetic and paragenetic states, and their possible evolutionary consequences. It is also interesting to consider that epigenetics may also revolutionize our understanding of biological evolution. Biological evolution fundamentally depends on the existence and nature of genetic variations. Many biologists, especially plant biologists, have long postulated that information may sometimes flow backward from the environment to the gene via epigenetic impositions on the genome. And have suggested the possibility for a generation of novel genetic variations. In the words of Barbara McClintock, might vary according the nature of challenge to be met. This seemingly radical suggestion led to a great deal of criticism and misunderstanding of McClintock. Unfair criticism, as I have argued previously. Rather than repeat the discussion here, I would refer the interested reader to Jürgensen 2004. This is, of course, the death of Jacques Monod and Jacob. The, I would say, perennial idea of a determined programming that is clean, original, and will make an individual. Here we even know that the environment can change the DNA. It's a field of possibilities, not something fixed, and not even something that only obtains to life. And it has the sameness of quantum mechanics, not being determined in advance. This is indeed biology go quantum. A field of possibilities is the same as the superposition It is no way of determining which genes are potential and which are actual, so to speak. In the system in itself, it doesn't differentiate. Why should it? I think there is a lingering idea that doesn't fit any area in science nor outside science, of a fixation that certain determined results, like the Laplacian determination of the whole universe in it, all directions, all trajectories and all potentialities will decide the next move. No. And of course this is radical, but this is actually what molecular biology is today. Nobody knows about it. I think everyone believes, including the people within intelligent design, that the genes decides life exactly, just like a Jacobian program. This is strictly not known, and the only admittance I heard, epigenetics may have some effects, which is absolutely untrue. It has all the effects, because truly not knowing what is potential or what is actually in the genes is exactly like the wave-particle duality. So you can say that the particle is the actual and the wave is the potential. They go hand in hand, and it can actually be the same gene, which is both potential and an actuality. My first idea when I read this is, wow, it means that the genome has a lot more perspectives. Turn that to the other way, that will also mean that there is a lot more of potentiality included. It can grow to a lot more difference. It is not truly decided, not fixated, if you like. This is more of an open structure where, well, you could say that the environment is the observer, and it sort of makes what happens happen. Not in a deterministic effect, but just like that. Epigenetics, of course, turned the table completely on the tradition of molecular biology. That's a positive evolution, I would say, to use a Darwinian expression, of biology. Maybe some questions here, Kalle?
So perhaps we could say that, we could say it stands both for the gene and particle. This is the dot. But the gene is also this, as Jorgensen points out. And this could stand also not only for the wave, but also for the environment in the sense, in the larger extended sense, environment. So wave and environment are more or less the same, metaphorically speaking. And here, I think also Richard Dawkins' idea about the selfish gene disappears. I don't know what he says about the gene and the environment, the milieu, but I suppose he follows Monod and Jacob faithfully. Definitely. So we could say, to simplify, up until Jacob and Monod, they have always focused on this, the dot, the smallest unit, while forgetting about the wave, the environment. Something that Jorgensen does not take up, and here I want to criticize him. I cannot take up everything, but he compares quantum physics with epigenetics, but he doesn't say anything about the observer's role in epigenetics. And he speaks about he speaks about the precise location. But my guess is that you cannot define the exact location only after observation, but perhaps future research will show that also epigenetics is the observer, which in one way or another influences the result. I would like to, I think this phrase, which begins page 3, is essential, but I don't quite get it because it includes a lot of difficult words that I want to ask you. In quantum mechanics, subatomic particles may be viewed in two different ways, that is, both waves and particles. Likewise, paramutations might be viewed both as gene expression states and as mitotically, and in some cases meiotically heritable states. So what does this mean in simple terms? This first phrase.
The first one is the undecided, and the second one is the heritage, which is the second one is more or less like Jack Monod or Dawkins.
Could you write them the explanations for the different words, difficult words?
The first one is the particle. This one is the first, and the second is, no, I have it wrong. The second is the gene particle, and the first is the wave of potentiality. This, where did you have it?
It's the first phrase of this. So you could say, so methodically.
Paramutations, that's the key word. Gene expression states that a possibility, and the other one is what we used to call the decided thing. So it carries both parts at the same time. This is a mix which is very close to the wave particle idea, where the particle is said to be more fixed, more Newtonian, where the other one is the wave of probability. There was another sentence here I was really keen on.
About probability or?
Well, it's giving more injury to the ideas of the primer biologists like Monod and Jacob. Biological, this is from the third page, last sentence. Biological evolution fundamentally depends on the existence and nature of genetic variations. So genetic variations is not a fault, it's actually necessary in that, so to speak, superposition. Many biologists, especially plant biologists, have long postulated that information can sometimes flow backward from the environment to the gene via epigenetic impositions on the genome. This is a bit like retrocausality, where something that happens afterwards, like the environment, changes the outcome and makes for what I think traditional geneticists would say, oh, that is pure chance, or something like that, something they didn't like. I think this is a death knell to the programming idea. Of course, well, I'm here comparing also to the sort of deconstruction that Derrida made, but this is more of a general tendency in all subjects. And the idea of a determinate state, like a recipe, if you go to a pharmacy and you have a recipe, you want the pharmacist to put that to every detail to make the same recipe, or in a cooking book. Sort of idea of exactness. I would say that that idea is part of Western logocentrism. But it's interesting how it enters into biology and made it previously one of those most fixed sciences, which is now opening up. Nature is undecided, which is not a fault. It is not a handicapped nature we're watching. It's a true nature that can work. Think of it. What would an organism be that is completely programmed deterministically? In a changing environment, it would be lost. It wouldn't even make any sense. And it stops slowly making sense to me more and more. It becomes a sort of a narrowed, fixed, static, stiff-necked, unwholesome way of watching at things. And it's a scale-wise. See here, we still have the particle, we still have the heritage. So it's not a turnover completely, it's not a not proving the previous investigations had been at fault, as Jörgensen really clearly points out. That goes both for Newtonian physics and traditional genetic biology. Maybe Kalle, you have some.
Since we have here Greek words, I will write down this in Greek, mythos, this is thread. And let me see, so here, if I understand correctly, this is the idea of identity. Yeah. So to say, I repeat this difficult sentence. In quantum mechanics, subatomic particles may be viewed in two different ways, that is both waves and particles. Likewise, permutations may be viewed both as gene expression states and as methodically.
Methodically and meiotically.
Mm-hmm. So methodically in this case it means that their cells are separated in two identical halves. And that is internal, something internal, so to say.
Internal.
Without the environment. Yes, okay, so I understood correctly. And this has always, this is the old view, or the programmatic view. So this is the program, so you have this genes follow a program. While the new view would be that they are also waves.
Well, both hold.
Yes, I suppose hold, of course, but this is the more the old view. But
yes. Yeah, correctly. Yeah.
But so could you say mythical is to simplify the thing, mathematically is the wave thing. Or no, it's
No, no,
it belongs to this.
yes.
Because this is, how would you explain it? They become smaller, etymologically speaking. They divide for each.
Yeah.
They become smaller and smaller, the genes. But where do you have the wave part here? Likewise, permutations may be both as gene expression states and as methodically.
Yes, the first one.
Methodically.
No, the first one.
Permutations, that is
Yeah.
that. Aha, okay. Okay, there is the. Okay, then I get it. I thought there was something. So you could say that genes are like permutations.
They're both metals and permutations.
So this is a definition of genes.
Yeah.
So the complex sentence would be like genes are permutations. That is like waves.
Yeah.
But genes are also like threads, so to say, and like so internal.
Yeah.
Yes. There was something else I was thinking about. Yes, the last sentence. Okay, we forget about this sentence. Now on the same page, the last phrase that you mentioned. Biological evolution fundamentally depends on the existence and nature of genetic variations. And here I was struck by the word variations, because I wanted to apply to my own field, New Testament textual criticism. And let's say, what is a variant? So you have old manuscripts of the Bible, and they have differences. So the biblical text is not uniform. Say you look Mark 1:41. One manuscript says that Jesus became angry. Another one says Jesus was compassionate. So these are two variants. So, and here, this shows that variation or variants, if you say so, are part of nature. So I think this is therefore necessary. So if the people say, no, you cannot have variants or variation, the life itself shows that. So that was the big takeaway, not a second great big takeaway. So that was everything from my side. If you want to say something.
Yeah, you're absolutely correct that without variations there is no nature at all. So it's like a third take on the idea of Monod or Jacob or Dawkins being correct. Nature wouldn't work that way, would come to a standstill. It is more obvious, it's more of a Western metaphysical fixation without an ideology that sort of will want to prioritize, for instance, the particle, and take away this, or see this as a deviation, which is actually what was in my biology book as late as of early 2000. So epigenetics was seen to be deviations. We know about them, but were deviations. Jürgenson is going a step further, say they're absolutely necessary. Without them, there is no nature at all, no life. This nicely goes back to Schrödinger. I think that was pretty marvelous to put everything in one short video. This is a difficult subject, but it managed. Thank you very much for your patience. Bye-bye.
Thank you.